Welcome to the office. We want to continue taking a look at cyclic groups, but actually we want to look at greatest common divisor still. So greatest common divisor, which we shared about in the last video, what we want to say is that if we have a greatest common divisor of 1, then we describe the two integers to be relatively prime. So two integers are relatively prime if their greatest common divisor is 1. So consider an example here. We have, we'll try to make things somewhat simple. 4 and let's see here. See, 4 and what else? I'm trying to think of something that's not trivial. 45. 4 and 45. Excellent. So 4 and 45 are relatively prime. We know that 4 is equal to 2 times 2, and that 45 can be written as 15 times 3. But that's 3 times 3 times 5, 3 times 15. So they have no prime factors in common. So their GCD is 1. The greatest common divisor is 1. All right. So what good is this? Well, if two positive integers r and s are relatively prime, okay, so relatively prime, r does not divide s, s does not divide r, okay, no factors in common, and r divides the product s times m, then r must divide m. So if s times m can be written as a multiple of r, then m must be a multiple of r. The way that we prove this, we're not going to go through a formal proof, partly because our textbook doesn't, but the way that we're going to take a look at this or justify it is through the way in which our greatest common divisor is defined. Our greatest common divisor is defined as the generator for this group where we take linear combinations. And if we're taking linear combinations, then the generator of that group must be a linear combination of those things. That is to say that if r and s are relatively prime, then we can create, so the fact that the greatest common divisor of r and s is equal to 1 implies that we can express 1 as 1 is equal to a linear combination of r and s. So let's see here. A times r plus, make sure I say the correct thing here. A times r plus b plus times s. Yep, that works. B times s. There we go. So there's a linear combination of r and s that gives us 1, where a and b are, of course, integers. Fantastic. So we have this greatest common divisor implies this. Oh, now what? Now I want to take both sides and multiply by m. So m is equal to m times a times r plus m times b times s. Now, what good does this do us? We have that r divides mar, r divides mar. That's pretty clear because it is already written as a multiple of r. Okay, and we know that r divides mbs because r divides sm, right? Integers, commutative here. R divides sm. So since it divides sm, it's certainly going to divide bsm. Or yep. Therefore, r divides mar plus mbs. But if it divides the entire right-hand side Hence, R must also divide the left side because they're equal. Hence, R divides M. Boom. R divides M. And that's all that we're looking for there. So this is a show, right? It's not the most prettiest, well-written thing that we would want to call a proof, but it has all of the key details that matter. The greatest common divisor is 1 because they're relatively prime. Since the greatest common divisor is 1, this implies that we can write 1 as a linear combination of them. Again, that algorithm for finding the the greatest common divisor, that algorithm actually gives a way to express the greatest common divisor as a linear combination of them. So that's fantastic. Anyway, once we have that, we multiply, we point out that, right, eventually the R divides this thing, therefore it has to divide that. We could clean it up a little bit, formalize it, and be able to express it in a proof format, and that would be fine. But I would not consider that a proof because it's just really not written as well as maybe it should be. Anyway, that's all I wanted to share for this video. Let's go ahead and continue on with the structure of cyclic groups in our next videos.